Welcome to Ask and Learn.
We want to sketch the graph of y is equal to 1 plus 1 over x plus 1 over x squared. Now, I went ahead and just added these up because this was really a rational function in disguise. And we might need to realize this is a rational function so we can start looking at horizontal and vertical asymptotes. Now, normally the first thing I would do is try to factor the top and bottom. But we know that x squared plus x plus 1 does not factor. So our numerator will never equal to 0. So we won't be able to factor and we won't be able to simplify this at all. All right, so first, in this chapter, it gives us a list of steps we should follow to sketch the graph of a function. The first one is to find the domain. Now, the only thing we will need to worry about is our denominator not being 0. So that would just be where x cannot be 0. So it would be negative infinity to 0, union 0 to infinity. Next, we want to find our intercepts. So intercepts. Now, we already said there's going to be no x-intercepts, just due to the fact our numerator cannot factor. And to find our y-intercepts, we're going to go ahead and let x equal to 0. So y-intercept is going to be 0 squared plus 0 plus 1 over 0, but that's undefined. So undefined, so there's no y-intercept either. So we're going to have no intercepts for our function. Next, we want to look for whether there's any symmetry. So rational functions aren't really known for being periodic. So we will instead to check to see if this is an even or odd function so we can determine if this is symmetric about the y-axis or the origin. So just plugging in negative x, we get negative x squared minus x plus 1 over negative x squared. Well, that's going to be x squared minus x plus 1 over x squared. And this here is not equal to negative f of x nor f of x. So that tells us we're going to have no symmetry, or at least no symmetry about the y-axis and origin. The next thing they tell us to look for are asymptotes. So we know when we have the same power, our horizontal asymptote will be just dividing the largest power's coefficients. So the limit as x approaches both positive and negative infinity of f of x is going to just be, well, the leading coefficient at the top is 1 and the bottom is 1. So it'll just be 1. Now, the limit as x approaches 0 from the right, and we want to look from the right because we'll have a vertical asymptote at x is equal to 0, since when we plug in 0, we would be dividing by 0. So of f of x. So let's just go ahead and plug this in. So 0 from the right squared plus 0 from the right plus 1 over 0 from the right squared. Now, if I square something that is slightly larger than 0, it's going to be positive. Something slightly larger than 0 will be positive, and 1 is positive. So adding all those up in the numerator, we'll have something that's positive in our numerator. And when I square something slightly larger than 0, that'll also be positive. So this here will approach positive infinity. Now we can look at the limit as x approaches 0 from the left of f of x. And so 0 from the left squared plus 0 from the left plus 1 over 0 from the left squared. All right. So just like before, we can go ahead and look at what happens here. So 0 from the left will be a slightly small negative number. Squaring that would make it positive. 0 from the left is going to be negative, and 1 is going to be negative. So now we know adding two positive numbers will be positive, and then we have to decide if adding something slightly smaller than 0 to 1 will make it negative. Well, if we make that term small enough, then it'll get dwarfed by 1, so we can go ahead and say that our numerator is going to be positive. And if we square something slightly to the left of 0, even though it's negative, it will become positive. So this will also go to positive infinity. So we have our asymptotes done. The next thing they suggest we find is our intervals of increasing and decreasing, and any local maxes or mins we may have. So we're going to need to find y prime. So let's go ahead and do that on the next page. So y is equal to 1. So for this, I'm going to use the original equation since I don't want to have to use quotient rule to take this derivative. You could use quotient rule and we'll get the same answer. I just want to be lazy when I do this. All right, so taking the derivative of this, the derivative of 1 is going to be 0. The derivative of 1 over x, so let's go ahead and rewrite this. So this is x to the negative first power and x to the negative second power. So to take the derivative of each of those, we use power rule. So it would be negative 1 x to the negative second power, and then plus negative 2 x to the negative third power. And then we can go ahead and rewrite this using a little bit of algebra as negative 1. And actually, I want to factor that negative out. So negative 1 over x plus 2 over x cubed. And then we can add those to get x plus 2 over x cubed. Oh, and this should have been x squared there. All right, so now let's go ahead and figure out where this function is equal to 0 at. So the denominator doesn't matter, so it only matters when the numerator is equal to 0. So we would do x plus 2 is equal to 0, or x is equal to negative 2. So this is one of our critical points, and also we get a critical point when our denominator is equal to 0, since it would be undefined. So x is equal to 0, but we know our original function x cannot be equal to 0. So we can just go ahead and ignore this. But keep in mind, normally when we have undefined points in our derivative, those are still critical. All right, so let's go ahead and use that. So we get y prime is equal to negative x plus 2 over x cubed. Now we want to determine where this function is strictly larger than 0 and strictly less than 0. So y prime will be strictly larger than 0, or this will be increasing when, so I went ahead and already solved this beforehand, just for the sake of brevity, and this would be negative 2 to 0 for when this function is decreasing. Next, we want to find where the function is decreasing, or when y prime is strictly less than 0. And again, I went ahead and solved this. So it would be negative infinity to negative 2 union 0 to infinity. All right, and so we only found one critical value before, being x is equal to negative 2. So to the left of negative 2, we would be on negative infinity to negative 2, and the function is decreasing there. And then on negative 2 to 0, the function is increasing. So this tells us x is equal to negative 2. So at x is equal to negative 2, this here will be a local minimum by using the first derivative test. All right. And then the next thing so this was supposed to be 5 and 6, not just 5. And then step 7, they tell us we should find our concavity as well as any inflection points. So we're going to need to know what y double prime is. So let's go back over here. And we have y double prime. So that's going to be the derivative of the first derivative. And again, I'm going to take the derivative of this when we distribute the x squared. Just because, once again, I don't want to have to do the quotient rule. So we can factor that negative out and then take the derivative of each of those. So 1 over x squared's derivative is going to be negative 2 over x cubed. Remember, just using the power rule again, just like we did before. And then plus negative 6 over x to the 4th. Now we can go ahead and distribute that negative, which would cancel those out. So plus, plus, plus. And then combining those into one fraction, we would get 2x plus 6 over x to the 4th. Now let's go ahead and set this equal to 0 to find our possible point of inflection. So again, the denominator can never make this equal to 0. So it would be 2x plus 6 is equal to 0, or x is equal to negative 3. And again, we would probably need to check our denominator, but in this case, since we know x is equal to cannot equal to 0 and it's also not in our domain, we don't need to worry about that point. All right, so let's go ahead and write our second derivative, which should be 2x plus 6 over x to the 4th. Now, this is going to be concave up when y double prime is strictly larger than 0. And again, I went ahead and solved this, and this should give us negative 3 to 0 union 0 to infinity. And it's going to be concave down when y double prime is strictly less than 0, which is going to be negative infinity to negative 3. Now we found that we have a possible point of inflection at x is equal to negative 3. So let's go ahead and check. So to the left of negative 3, this function is concave down. And to the right of negative 3, this will be concave up. So this is indeed a point of inflection. All right, now that we have all that, the next thing they tell us we should do is go ahead and graph. All right, so we are told we have no intercepts. We have no symmetry. So let's go ahead and plot our asymptotes. So we found the end behavior supposed to go to 1, so we have a horizontal asymptote, at y is equal to 1. So y is equal to 1. And we have a vertical asymptote at x is equal to 0. And to the right of 0, we know we are approaching positive infinity. And also to the left of 0, we know we're approaching positive infinity. Next, we know we're going to have a minimum at x is equal to negative 2. So negative 2. And we're going to have a point of inflection at x is equal to negative 3. So those points are going to be important. So let's go ahead and start to the right of our graph. So to the right of 0, we have no maxes, mins, no inflection points. So we know we just need to approach our horizontal asymptote. And we'll approach it from above. Next, we know at x is equal to negative 2, we're going to have some kind of minimum here. Let me go ahead and put that to red, actually. So we'll have some minimum here. So it's going to come like this and hit x is equal to negative 2. And then by the time we hit negative 3, it should be going from concave up to concave down. So it should look something kind of like this here. And we'll keep getting closer and closer to y is equal to 1. And actually, let's go ahead and find what y is equal to negative 2 should be, because maybe we actually do go below our horizontal asymptote. So let's go ahead and find that over here. So f of negative 2 is going to equal to 4 minus 2 plus 1 over 4. So it's going to be 3/4. So actually we do dip below. So let me go ahead and actually fix this. So here we have our minimum, and we go and we dip below our horizontal asymptote, and then we're going to come back up and then get very close to our horizontal asymptote from the bottom. So if you have maxes and mins, it is a good idea to go and check it, because otherwise you might do what I wanted to do at first and kind of not notice that we should be going below the horizontal axis here. And we could maybe put some values for some of the points, but since we're just sketching it, I think that's all that really matters for us.